Welcome to Management 670. Today I want to talk about probability and odds. Let's get started. Basic probability. What is probability? Probability is a value somewhere between 0 and 1 inclusive, so something can be 0 or 1, that describes the possibility that an event will occur. Sometimes call this a measure of likelihood of an event. An experiment here is different than setting up a chemistry experiment or even a data experiment. This is thought of as just the process of obtaining value, some kinds of values here, in what we call as observations, outcomes, or maybe even just simple events. An outcome is the result of an experiment. We'll do a couple examples here in a minute. And the last piece of technical jargon I want to say is sample space. That's the collection of all of the possible outcomes. And a note about sample space is that the experimenter, the person creating this experiment, can decide the length and number and type of answers in the sample space. So for example, if we're tossing a coin and we just want to record the face, whether it's heads or tails, then it's simple enough to see that the sample space is heads and tails, those two together. But if we're observing somebody buying a soft drink, maybe at a restaurant, and we want to categorize it on behalf from a Coca-Cola perspective, we could say Coke or lump everything else together in other soft drinks. If we could, some other experimenter or for some other purpose might want to categorize the sample space as Coke and Pepsi and root beer and alcoholic drinks and then everything else. We can talk about multiple observations in a row. So if I toss 2 coins up in the air and I record the faces, then we could use some shorthands and see the 4 possible sample spaces, all the different observations that are available in that sample space. Both are heads, HH. First was heads, the second was tails, HT. Reverse of that was tails first and then heads, and then tails twice, TT. Same with purchasing soft drinks. If we code Coke as C and other as O, then CC, CO, OC, and OO is the entire sample space for the experiment of purchasing 2 soft drinks. It doesn't have to be something silly like that. It could be a business process like inspecting a part and just noting the quality. And we could define that sample space as defective or good. 2 important properties that are often discussed with probability are mutually exclusive and collective exhaustive. Mutually exclusive is when 2 outcomes cannot occur at the exact same time. In that experiment of flipping 1 coin, we would say that the observed value has to be heads or tails, but not both. A loan applicant, when applying for a loan for a bank, can say that they are both a college graduate and not a college graduate. We say that those are mutually exclusive and cannot exist at the same time. Collective exhaustive is the set of all events that account for the outcomes in a sample space. For example, if you roll a fair 6-sided die, only 1 of 6 outcomes can be recorded from it. 1, 2, 3, 4, 5, or 6. Those 6 values represent the entire space for it. So there's a 100% probability that 1 of those 6 will be recorded. Let's look at an example here. It's a cross-tabulation and contingency table. Let's say a store wanted to analyze the last 100 purchases of DVDs and televisions and came up with the following table. So the 3 types of televisions that are sold are regular, flat screen, and then HD TV. And then for DVD, they either purchased one or they did not. In the 6 green shaded areas, we call those joint probabilities. That's the probability that both of those actions happen. So the very top one, so 20 out of the 100 people bought a regular television and did not buy a DVD. This is in contrast to the 5 yellow shaded cells right there. Those are what's known as the marginal probability values. They are the sum across the rows or the columns. So if we just looked at TVs, for instance, 25 out of 100 purchased a regular television, 35 out of 100 bought a flat screen, and 40 bought an HD TV. The marginal probabilities add up to 100% for the given characteristic. So the 3 television add up to 100. The 2 values, the 2 marginal probabilities for the DVDs, add up to 100 as well. This table is mutually exclusive and collectively exhaustive. We have a general form here and introduce some notation. The P in front of those joint probabilities is for probability. A1 is the first type of event A, and A2 is the second subset of event A. Same with B1 and B2. That joint probability P, A1 and B1 means the number of records where A1 happened and B1 happened. Marginal probability is just the probability of B1 happening. So we say that was probability and then B1. The sum of the marginal probabilities, whether by row or by column, does add up to 100%. That's why the collectively exhaustive comes in. Let's do a couple of problems. What's the probability that a customer purchased an HD TV? See the HD TV column? We'd say that that's the marginal probability of HD TV. That is 40 out of the possible 100. We say the probability is 40%, or 0.4. What is the probability that a customer purchased a DVD player? This time, instead of looking at the column, we're going to look at the row for yes for DVD. I see the marginal probability is 60 over 100. That's 60%, or 0.6. What is the probability that a customer purchased a flat screen television and a DVD together? Now, this is a joint probability that shows flat screen, that column, followed by the row for yes. We find that intersection has a value of 25. It's 25 out of 100. We say that's 25%, or 0.25. And finally, what is the probability that a customer purchased an HD television or a DVD player? Notice when I add the columns for the HD TV, that's 40. It's the marginal probability for the HD television. I find the marginal probability of yes for purchasing a DVD. That's 60%, or 60 out of 100. But when you add those together, that would be 100%, which is incorrect. So you don't just add the marginal probabilities for this section. We add the marginal probabilities for this question and then subtract off the joint probability. We'll get to that property in a second, but 10 and 30, 5 and 25 are the values here in these four cells. That adds up to 70%, or 70 over 100. Now I want to talk about conditional probability. That's the probability of an event occurring given that some other event has happened already. Conditional probability of A, given that B has already happened, is denoted as P for the probability of A occurring. There's a vertical line right there that shows its conditional probability, given B has already happened. In fact, this conditional probability has the formula written at the bottom of the slide, which says A given B, that conditional probability, is the probability of A and B occurring, so that joint probability, divided by the probability of B. So let's do an example. Given a customer purchased an HD TV, so it already happened, what is the probability that the customer also purchased a DVD player? Well, given the fact that 40 out of 100 people purchased an HD television, that is our probability of B in this case. So given that that's already occurred, that's the marginal probability. Then I want to divide that joint probability where it's an HD TV and a DVD player, and I see that 30 right there. So the conditional probability of somebody purchasing a DVD player, given the fact that they purchased an HD television, is 30 divided by 40, or 0.75, 75%. Two laws that apply for probabilities here. We have the addition law, which is the fourth question from the previous slide. Provides a way to compute the probability of two events when either can occur. We write it as the union of probability of A and B, and we subtract that joint probability. We don't want to double count it, in other words. Next, we have the multiplication law. That's when the intersection of two events occurs. That means both of them have to happen. We say that's the intersection of probability A and the upside down U of B. That is the probability of B multiplied by the conditional probability of A given B, which is also equal to the probability of A multiplied by the conditional probability of B given that A has already occurred. This is useful for determining if two events are independent of one another. Back to a measure of association, but through a lens of probability. An occurrence of an event does not affect the probability of another event. We would then say that they are independent. So the conditional probability of A given B is just the probability of A if they are independent. That's one way to prove statistical independence. We also have the multiplication law for independent events, and that is if the probability of A and B happening is just the product of the marginal probabilities of A and B. They are equivalent and sufficient proof to say that these two events are statistically independent. I want to throw out a practice problem here that I'll cover in another video, but are the DVD purchases statistically independent of the types of televisions purchased? Does the probability of a customer purchasing a DVD player depend on the type of television that the customer has already purchased? We'll give you a few moments. We'll cover that in another video. Finally, I want to wrap up this section by Bayes' theorem. Usually when we start the probability analysis, we have to make some initial assumptions. We call these prior probabilities. They're our best guesses or based off of historic trends. From the sample, special report, the test, or the experiment, whatever it is, then we receive more information. Then we go back and take a look at what the actual probabilities were, or the posterior probabilities. The Bayes' theorem provides the means for actually going back and determining, revising these prior probabilities. Here's the formula itself. As you can see, it is based off of the conditional probabilities of A and B. And in a separate video, I'll show you an example. So in conclusion, probability is a numeric value between 0 and 1 given to an event occurring. And there are many properties based off of those.